there's an important concept that relates to vectors that you need to understand. And that is the concept of linear dependence. And also, oops, this is not an N, this is an R. Linear, that's an R. The related concept is a linear independence. And these two terms refer to a relationship between a set of vectors. Okay, suppose we have
Text message only, text message only. You're in the same police department. This is a text message only of the emergency system. This is a text message only.
Okay, so suppose we have a set of vectors.
2000. This is a text message only.
And each of these vectors will be denoted by the lowercase letter v. V sub 1 is the first vector. Okay, that's a lowercase v. V sub 2 is the second vector. Dot, dot, dot. And the last vector is v sub n. So you have n vectors. Now, it's assumed that the dimension of each of these vectors is the same. They all could be 2 by 1s or 3 by 1s, or et cetera. But all of these vectors are assumed to have the same dimensions. Now, this set of vectors is said to be linearly dependent if any one of the vectors can be expressed as a linear combination of the remaining vectors. Okay. Now, that definition is taken right out of the book on page 62. So let me just repeat it again. I'm not going to write it out because it takes a long time, and it's right in your book on page 62. A set of vectors, v1, comma, v2, dot, 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 vn, is said to be linearly dependent if and only if any one of them can be expressed as a linear combination of the remaining vectors. Let me illustrate this with a simple illustration. And I'll take this example right out of the book. Suppose we have these three vectors. v1 is a 2 by 1 vector equal to 2, 7. v2 is another vector equal to 1, 8. And v3 is a third vector equal to 4, 5. Now, if one of these vectors, in fact, if any of these vectors can be, any of these three vectors can be expressed as a linear combination of the other two, then the set of vectors is said to be linearly dependent. Now, in this case, it's easy to show that you can write v3, and by a linear combination, I just mean v3 is a linear combination of v1 and v2. If you could write the following, k1 times v1 plus k2 times v2, where k1 and k2 are any constants, any scalars. Okay. If you could find scalars, k1 and k2, that will make this statement true, then V3 is said to be a linear combination of V1 and V2. Can you find the values that would work for that? Notice V3 is this, 4, 5, isn't it? And V1 is this. V2 is this. Okay. Can you find, and the book is kind, they're actually whole numbers. They wouldn't have to be, but in this example, they're actually whole numbers. Can you find whole numbers for K1 and K2 that'll make this statement true? Anybody? Find whole numbers, K1 and K2, that'll make this statement true. We'll just concentrate on this top one first. Can you find values of K1 and K2 that would make that top statement true? In other words, 4 must equal 2K1 plus 1K2. Yes?
Could you do K1 as 3 and K2 as negative 2?
Okay. That would work, wouldn't it? Because this would be 6 minus 2 equals 4. So let's try that. K1 equals 3. K2 equals minus 2. That will work for the top. Let's see, does it work for the bottom? 3 times 7 is 21. Minus 16. Bingo, it works for both. Very good, you got it. So we have found values for K1 and K2 that make this statement true. Therefore, we know that one of the vectors can be expressed as a linear combination of the other two. In fact, if you just find one, that's enough, because it turns out that all of them are a linear combination of the other two, because all you have to do is manipulate them to get that. Notice, let me just illustrate that. Here we have shown this. And now just substitute in, this is 3. This is minus 2. But we could solve for V2 as a function of V1 and V3 just by getting it over on the left-hand side. Notice we could rewrite this equation right here as 2V2 equals 3V1 minus V3. And now divide both sides by 2, and you get a V2 equals 1.5 V1 minus 0.5 V3. Now in this case, they're not whole numbers, but that's okay. They don't have to be whole numbers. Okay. In a similar fashion, we could solve for V1 as a function of V2 and V3, doing something similar. So, in fact, we could say for this set of vectors, any one of the 3 vectors could be expressed as the linear combination of the other 2. Therefore, the set of vectors is to be linearly dependent. Now, if you could not express one of the vectors as a linear combination of the remaining vectors, then the vectors are said to be linearly independent. Okay. But in this case, they're linearly dependent. But if you could not find an equation of this form, then they would be linearly independent. Okay.